All right. Good morning, good day, good afternoon, good evening. Uh, Here we are, and we're starting off with some physics. Well, this is physics, so of course we're starting with physics. But what we're doing here is get my pen set up right. We're taking a look at Newton's laws of motion. Now, this corresponds to chapter 6, but not that you have a textbook for that to make any sense. So anyways, we're taking a look at Newton's laws of motion, and we're continuing from there. Right. Yeah, we learned today that Newton first proposed these back in 1687. Like, that's a long time ago. Uh, he was a pretty smart dude. And return you to that quote that he only laughed once in his life. Anyways, what these laws of motion do is that they give us a way to take a look at the world around us and to analyze the world around us in terms of forces and motions, accelerations, and so on. And so it's sort of the framework that we can use to understand how the world works. So let's take a look. This first law is what we call the law of inertia. And well, really often this is set down that an object at rest remains at rest. Now, that is pretty straightforward. Like, take a look at your computer that's sitting in front of you on the table. It remains at rest. If it suddenly flew across the room, you'd be wondering what caused it to fly across the room. We're not expecting it to fly across the room. And it's, sometimes you see pictures, movies that take where the camera's inside the cabin of a ship, and you see things moving across the table and so on. Well, they're moving across the table, but something's causing them to move across the table. We just can't see the rocking of the ship because the camera's fixed to it. So an object at rest remains at rest. That's what we often deal with as inertia. But an object in motion remains in motion. An object at rest remains at rest. An object in motion remains in motion, traveling in a straight line. With constant velocity. This second part is kind of a part that we don't often sort of think about. We can understand an object where rest remains at rest, but an object in motion remains in motion. Well, we don't really see that. And you're driving in a car, you take your foot off the accelerator, you come to a stop. Things slow down, and so how does that fit? How does that fit? And we'll get into that. But this is what Newton's law states. Now, I bring to remembrance, because I've done this several times at school, where we have a table and have a bowling ball. And, whether it's Tammy or some other bowling ball, it's rolling along the table and it falls off the table. Boom, boom. And then it continues rolling along the floor. And the velocity that it has up here is equal to the velocity that it has down below. And so I just bring that to your remembrance because it does give us an idea of that this is how things work. A bowling ball, once it's moving across the table, continues moving across the table. And even when it falls off the table, it continues moving along the floor. And that we can tell that the velocity is basically the same. When does the bowling ball stop? Well, when it runs into something, somebody's foot, somebody's bag, a chair, and so on. And so we get the idea of this is how, well, this is what the law of inertia is stating. Now, Newton's second law, and these are all sort of related together, but Newton's second law is like an unbalanced force. We're going to be talking a lot about balance of forces, but an unbalanced force, and we're going to call this a net force, will cause, so an unbalanced force will cause an acceleration in proportion, nope, spelling wrong, in proportion to its mass. And a lot of times what we'll do is we'll express this as F net is equal to ma. And so this is where our calculations and so on will come in as we take a look at this. And pretty simple, force is equal to mass times acceleration. Or if we're given force, given what its mass is, that determines what the acceleration of that object will be. The larger the mass, the smaller the acceleration for a given force. It's really that easy. And then we have his third law. For every action, there is an equal and opposite or but opposite reaction. This is sometimes expressed. Forces come in pairs. You can't touch without being touched. Oh, isn't that a nice way of putting it? You know, forces come in pairs. You know, it's like, I was going to say, when Mahak and Isha have a fight and one of them punches the other in the face. Well, the face feels a force, but so does the fist, you know. So you can, you know, the forces here, the force against the face and a force against the fist are going to be the same amount of force. For every action, there's an equal and opposite reaction. Just picking on Mehek and Isha because why not? All right, so free body diagrams. This is where we're going to take a look. These are actually really kind of fun. I'm going to go through a bunch of them with you, and then there's a worksheet that will be available for you to do. But basically, we're taking a look at where are the forces. And are they unbalanced? So let's continue on, shall we? All right, so free body diagrams, FBDs. Now, it's really important that you have some exactitude of drawing skills. Like, that's all there is to it. You know, I'm a pretty good drawer at times. You'll sometimes comment, oh, you should do that as an art. Anyways, so a book is at rest on a tabletop, a free body diagram. So we have a tabletop, and there's draw book. There's our book. Woo woo. When I say that you need drawing skills, I'm completely joking. But we want to take a look at this diagram. So the book is at rest. Now, on a tabletop, where's the tabletop? It's on Earth. That's going to be pretty much a given. So if we're on Earth, we have a force of gravity coming down. All right, there's our force of gravity. Now, is it accelerating? Is it moving? No, it's at rest. And so there has to be an equal and opposite, and we call that our normal force, perpendicular to the surface. There's our book at rest on the tabletop. If we were to have it at rest on the slope, we again draw our tabletop on a slope, and there's our object. All right. So we are on Earth, so we're going to have force of gravity. Force of gravity comes down. If I have to ask a question, what are the forces? The first answer should always be force of gravity. We're going to have a normal force. Our normal force is perpendicular to the surface. It's going up. These are not equal to each other. And then we're also going to have a force of friction. And you might say, well, okay, why is there a force of friction? And I'd say, well, doesn't this block want to move down? And you would say, yes, it wants to move down. That's the slope. But where's the force that's moving it down the slope? We don't see it. There's no force down the slope. So you're right. But sir, let's take a look. I just want to expand this. So when we have this, here's our force of gravity. And here is our normal force. What I want you to understand is that this force of gravity here is going to be broken up into two components. We're going to have this component here, which is going to have the same value there. And then we've got this value here, which is what we'd call, say, the force down. And that's the force that is causing it to slide down. And those come about from the force of gravity and this angle. So this would be our force of gravity, and it's the adjacent, so that's cosine of theta. And this would be our force of gravity, sine of theta. Now, I'm not going to be having you do these types of questions. I'm just pointing this out to you, because then we can go back and understand that we have this force of gravity going up the hill because this force down is trying to move it down the hill. And so if the force of down the hill is less than the force of friction, this is force of gravity, it's supposed to be force of friction. If this force of gravity, the portion going down the hill is less than the force of friction, then this doesn't move. If the force that's going down the hill is greater than the force of friction, then it will move. That's really all there is to it. Anyways, I point this out, but I remind you, this is Physics 12. All right, let's go to the next page. A girl is suspended motionless from a bar which hangs from the ceiling by two ropes. Okay, first of all, we need to draw a picture of a girl. There's our picture of the girl. I got to change this. Come on. And there's a picture of the girl. Now, picture the girl is hanging from a bar. Okay, so we're going to have the force of gravity coming down because we always have the force of gravity. And now she's hanging. So there's going to be what we call a force of tension. And the tension is in her arms. And these two forces are going to be balanced because she's just hanging there. Now, if we wanted to, we could perhaps, yeah, no, this is really as good as what we would want to show. Because that she's hanging from a bar. I mean, if we wanted to show the bar, then we would show a force going up and a force going up and a force going down. And this would be our force tension here, and these would be our two forces going up. Is what that, so various things that we can see that these two forces have to add up to what the force of tension is. But really the key thing for our free body diagram and the analysis is that we have a force of gravity with the tension that's going upwards. All right, an egg is in free fall from a nest in the tree. Neglect air resistance. All right, so let's draw our egg. There is our egg. Excellent. Yeah, cool. Now, what forces do we have acting on this? Well, we've got the force of gravity, first answer, going down. And but what about the normal force? We've got the normal force going up. No, it's free falling. And if it's free falling, is it uniform motion? Is it not moving? No, it's accelerating. And this is not equal to zero. And so there's going to be an acceleration going on. And it says neglect air resistance. Air resistance is like friction due to the air. And if there is no, so F friction of the air is equal to zero. And so that we're going to have nothing that is opposing the motion. All we're going to have is the object with an unbalanced force. So this is an unbalanced force. And there's going to be an acceleration that's happening. All right, let's continue on. A flying squirrel, no wing flap, is gliding from a tree to the ground at a constant velocity. Consider air resistance. Well, we're going to make this really simple. First of all, I should have done this. And that would be to take a look at a flying squirrel. Well, okay, let's just draw a flying squirrel. I'm sure you've probably seen them on TV. So here's our flying squirrel. Okay, here's our flying squirrel. And it's gliding from tree to tree. Well, tree to the ground. So it's going from the tree to the ground, which means that there's a force of gravity acting on it. And that there's air resistance. Well, let's say it's gliding from the tree to the ground. It's just dropping straight down, but so there's going to be some air resistance going up. Now, let's call this F air. Now, if what's the situation here? Well, we can have a situation where F air is equal to Fg. And this is what we would call terminal velocity. Now, this has nothing to do with dying, hopefully. But in terminal velocity, what we have is we have balanced forces. The force of gravity and the force of the air resistance are equal to each other. Now, in a skydiver, if somebody's jumping out of a plane and they're skydiving, you're going to have them and they're going to be there and they're going to have their feet up and their arms up. And so they're falling and they will reach a terminal velocity where they're not going any faster. And then they pull their parachute and then they come down and they're going to have a slower terminal velocity because they have much more air resistance. And they're going to get to a situation where they're not accelerating. And so the velocity will be slower than here. So terminal velocity relates to the complications of air resistance. By changing your pattern, how you present yourself to the air, you can slow yourself down or you can make yourself go faster. So if the air resistance is equal to the force of gravity, then you're not moving faster. If the air resistance is less than the force of gravity, unbalanced force, so then our acceleration is not going to be equal to zero. And so when you jump initially out of the plane, there is no air resistance, since the force of gravity is much larger, and so you're accelerating. And so you have to accelerate for a certain time until you come to this terminal velocity. Okay. Can you think of a situation where the air resistance might be greater than the force of gravity? What's going to happen then? A rightward force is applied to a book in order to move it across the desk with a rightward acceleration. Consider the forces of gravity. Okay, first of all, let's draw our table. Then let's draw our book. Let's consider the forces. Is there a force of gravity? Yes, there's always going to be a force of gravity. We have a force of gravity that's going that way. So we have a force of gravity. Well, frictional forces, there has to be a normal force. So we're going to have a normal force. These are going to be equal and opposite balance. It's not moving down through the table. It's not lifting up on the table. We're providing a force towards the right. So we're going to have a force towards the right, and we'll call that force push. And we have an acceleration that is not equal to 0. So we're going to have a force of friction in the direction opposite, but my force of friction, I'm going to draw as a shorter arrow because it's there. It's less than the force of push, but it's unbalanced. These are not equal to each other. These two are equal to each other in the vertical. These are unequal in the horizontal. There's going to be motion. There's going to be acceleration in the horizontal. The acceleration is not going to be equal to 0. All right. A rightward force is applied to a book in order to move it across the desk at a constant velocity. Okay, we pull out our artist capabilities. There's my book. What forces do we have? Well, we got the force of gravity. Excellent. We've got our normal force. Excellent. Those forces are going to be equal and opposite. It's not moving down into the table. It's not bounding off the book. We're applying a force to it. There's my force of my push or my pull. I'm moving it across the table. But it's at a constant velocity. If it's constant velocity, uniform motion, the acceleration is equal to 0. And if the acceleration is equal to 0, then my force of friction has to be equal to my force of my push. That's what we mean by this situation. Consider frictional forces, neglect air resistance. Now, neglecting air resistance is going to be the normal frame. We're generally going to ignore the air resistance. Frictional contact forces are going to be more important. Normal forces, air resistance not going to be, unless we're traveling, high speed. So jumping out of an airplane and so on, we reach velocities that are going to be. All right, a college student rests the backpack on his shoulder. The pack is suspended by one strap from his shoulder. A free body diagram for the situation. It's motionless. If it's motionless, the velocity is equal to 0. The velocity is equal to 0. Acceleration is equal to 0. So first of all, let's draw the backpack. What forces do we have acting on it? Well, we have the force of gravity. Is it sitting on a table or anything like that? No, it's being hung. So there's no normal force, but what we are going to have is a force of tension that is in this strap. And those are going to be equal and opposite. It just looks like that. Really not that big. Skydiver. I knew this one was coming up. A skydiver is descending with constant velocity. Consider the air resistance. First of all, let's draw our skydiver. You're getting the point. And we're going to have there's my force of gravity. Then I'm going to have a force going up. Constant velocity, acceleration is equal to 0. Forces are balanced. Net force, we would say, is equal to 0. Forces balanced. And so we're going to have a force, let's call it F air, that's going up. And these two forces are going to be equal to each other. Forces are balanced. Net force is equal to 0. Acceleration is equal to 0. A force is applied to the right to drag a sled across loosely packed snow with a rightward acceleration. Okay, first there's our snowfall. Here's our sled. And here, well, let's consider the forces acting on it. Do you have a force of gravity? Of course we have a force of gravity acting on it. Is there a normal force? Of course there's a normal force. How do those forces relate to each other? Is it plowing into the snow? Is it flying up off of the ground? No. Well, then these two forces, the normal force and the force of gravity, are going to be equal to each other. We are dragging the sled with a rightward acceleration. So we're dragging this way. So let's go force pull. Doesn't really matter, but we're providing a force in that direction. And we're going to have a force in the opposite direction. That's going to be our force of friction. Unbalanced. So F net is not equal to zero. The acceleration is not equal to zero. These forces are not balanced. The force of the pull, F pull, is not equal to the force of friction. Okay? Are you beginning to see what we do? We're taking a statement like this, and we're analyzing that statement in terms of the forces that we know are acting on it. Force of gravity, normal forces. So our vertical forces and our horizontal forces. And that's going to be really the nature of this. And when we find unbalanced forces, then we're going to be applying these things, the idea of the net force not being equal to zero. All right, a car. Oh, a car. Wonder what type of car. Okay, a car is coasting to the right and slowing down. Okay, so here's my car. Yeah, there's my force of gravity. If I have a force of gravity, it's on the road. I have a normal force. How does the normal force relate to the force of gravity? Well, is the truck plowing into the ground? No. Is the truck flying up off of the ground, or the vehicle flying up off the ground? No. Then the normal force and the force of gravity, they're going to be equal to each other. There's no acceleration or anything like that. The car is coasting towards the right. So is there a force that's pushing it towards the right? No. And I bring you back to Newton's first law. An object in motion remains in motion, traveling in a straight line. Inertia keeps it going. And so, but it's slowing down. Well, so if it's traveling towards the right, then there's going to have to be a force of friction that's traveling towards the left. So these are the forces that are going to be there. Is there going to be an acceleration? Yes. So A will not be equal to zero. And we could calculate that acceleration in terms of the unbalanced force. Okay, inertia. Um, and that's it. Yeah, if you remember from Bill Nye, if you listen to the tune of Bill Nye's, the intro to each Bill Nye show, it often says inertia is a property of matter. And we can think of it actually of inertia as being a measurement of matter, of mass. Now, this is kind of a strange idea. But, if we are, uh, you know, here on Earth, and you can think of a box, and you can come around, you can bend your knees, and you can pick up that box. Or you can come along and you can have a bigger box and try to lift it up. Well, here you might be able to, here you won't be able to, because it has larger mass. It's heavier. We can lift up a box of Christmas ornaments, but it's pretty hard to pick up a truck, a car, different masses. Well, let's go for it into outer space, into orbit. Woo! And if we take a look inside our space station, here we have our box, and it's in free fall, so it's floating. Here we have our astronaut. Can they pick up the box? They can hang on to the box. They can be part of the box. Can they pick it up? They can apply forces to the box. Sure, no problem. Well, what about if we had our Tesla vehicle? Could Elon Musk come along and, just hang on to the side of his vehicle? Yes. So whether it's a box or whether it's a car, you can pick that up in essence in outer space. You can hang on to it in outer space in orbit where things are in free fall. And because there is no, in essence, no no gravity. I don't want to say no gravity. This isn't even correct to say no gravity force detected, but we're in free fall, so everything is falling at the same rate inside our space station. And if we're inside the space station, the idea of picking up some books and so on doesn't make a lot of sense. But if you come up to this box of Christmas ornaments and you push the box of Christmas ornaments, what's going to happen? Well, it's going to fly across the room, and you're going to fly backwards a little bit, but they're going to be moving across. Well, if you come into this car and try and push the car across, well, the car will move, but you're going to be moving more so as well. This has greater inertia than the box. This has greater mass than the box. And when something has greater inertia, it's going to take more force. It has greater mass. It's going to take more force in order to accelerate that object. So in free fall, we don't really have any weight, but the idea of inertia being a property of matter, being a measure of the matter, is kind of what I'm talking about here. Anywho, enough of me talking. So there is a worksheet on free body diagrams, and you can take a look at that and do that, and then I will post a video solution to those. That's probably the best way, but I don't think you're going to find a lot of problem. And then we'll start doing some uh, solution or some questions. It This is kind of fun. Sir, you're a geek. Yes, I know. Uh, but these things are kind of fun, and they're not necessarily that difficult. It just takes some computation, so I'm going through. Anyways, hey, nice chatting with you guys today. I hope you guys are doing well. And had a question earlier today, and it was the quiz. It hadn't said that you could do it twice. And this is the one on forces with friction and springs. And yeah, you still can do it twice. It just didn't say that you could do it twice. And I just see you could do it probably. I would wonder if you could try it 3 times, whether it would kick you out or not. Because there's really not a registration. You're putting your name in there, and that name is just letting me know that it's you. So it'd be interesting. I put a lock of 2 times doing the quiz on there. Not that it's really going to matter, because I just when I see the name, and then I take a look and see how you did and record your marks appropriately. Um, but yeah. Anyways, that's all for now. So you're always going to be able to do them twice. You can make your corrections and show you the questions you've done incorrectly. It just doesn't tell you what the correct answer is. I want you to rethink about the question and do better on it. Okay. As always, you can see me on Jitsi. Most of the time, unless I'm recording something like this, then I'll have Jitsi turned off. You can send emails. Those are always work as well. And hey, just, if you have got questions, let me know what's going on. I'll do my best to help you. All right. Take care. Have a good rest of your day.